Taylor series application in the special theory of relativity. Einstein's special theory of relativity states that the mass of a moving object with the velocity v is given by this equation. So mass is equal to uh, raised mass over the square root of 1 minus v squared over c squared. So where m sub 0 here is the mass of the object at rest and c is the speed of light. And the difference between the total energy and the kinetic energy, the difference between the total energy and the energy at rest is given by this. So we have illustrative example here. So if velocity v is very small relative to c, the speed of light, the k here becomes one half of the product of the wrist mass and the square of the velocity here, is square of the speed of the moving object here, according to Newtonian mechanics. Then letter B, estimate the difference between the relativistic and Newtonian expression for p, where the magnitude of the velocity is less than or equal to 100 meters per second. So we have the solution for letter A here, classical limit of relativistic kinetic energy. The relativistic kinetic energy is given by these equations. So gamma minus 1 times the rest energy here, where the gamma here is equal to 1 over the square root of 1 minus p squared over c squared. Now for the speed of the moving object, much less than the speed of light, define x equal to v squared over c squared. So x here is much less than 1. So using the binomial expansion for 1 minus x raised to the negative 1 half, this is the binomial expansion here. Then I'm subtracting 1 and multiplying by m by the rest energy here. So we have these expressions. So when the velocity is much less than the velocity or the speed of the moving object is much less than the speed of light, higher order terms like v to the 4 over c to the 4 are negligible. Thus, the kinetic energy now becomes 1 half of the m sub 0 v squared. So this is the uh, energy according to the change in energy according to change in the kinetic energy according to Newtonian, according to classical Newtonian physics. So this matches the classical Newtonian expression for kinetic energy. Now for letter B, estimating the difference using Taylor's inequality. We aim to estimate the difference between the relativistic and classical expression for K when the magnitude of speed of the moving object is less than or equal to 100 meters per second. So the classical expression is one half classical expression for the uh, kinetic energy is equal to one half of the rest mass times the square of the speed of the moving object. So the relativistic expression includes higher order corrections. So the relativistic kinetic energy here is one half m sub 0 v squared plus 3 over 8 m sub 0 v to the fourth c, uh, c squared v to the fourth c squared. So let t here v squared over c squared. Then the relativistic kinetic energy here is uh, rest energy times 1 minus t raised to the negative 1 half minus 1. So we have to define here. Now let's define d of t equal to 1 minus t raised to the negative 1 half minus 1. Now, actually, we are going to use the Maclaurin series here at t equals to 0 here. So a Maclaurin series is a specific type of Taylor series that represent a function as an infinite sum of terms calculated from the values of the function's derivative at a single point, specifically at h equals to 0. So essentially, it is a way to approximate the complex function like sines, exponential, or square roots using a simple polynomial. So we have the general formula here. The Maclaurin series for functions f of x given by this f of x equal to f of 0 times the first derivative of f of 0 times x. Then we have the second derivative of uh, function where x here is equal to 0, and we have the 2 over the 2 factorial times x squared. Actually, this comes from the zero series. We just make the x here equal function of x as equal to f of of f of 0. For example, the third derivative of the where x here is equal to 0 over the 3 factorial times x cubed. Then up to n derivative of f of 0 over n factorial times x to the n. Or more compact sigma notations, f of x equal to the summation from n equal to 0 to n equal to infinity. So the n derivative of f of 0 over n factorial times x to the n. So we expand the g of t around the t of 0 here. So this is already the Maclaurin series, t equal to 0. So this is also a type of this is also a subset of the Taylor series. When t here becomes 0, the Taylor series becomes the Maclaurin series. So the first degree polynomial is 1/2 of t. And the remainder after the first degree term is g of t minus p1 of t. Then using Taylor's inequality here, so the second derivative of g, the absolute value of that is less than or equal to m on the 0 to t. Then the first remainder here is equal to m over 2 factorial. So the 2 factorial here is, this comes from the Taylor series formula. And we have the t squared here. So the second derivative means we have, it also means the second derivative for the square of 2. Compute the second derivative of t of t here. We have t here is b squared over c squared. And this is less than, so the speed of the moving object is less than 100. We have the c squared here, the speed of light. So approximately we have 1 minus t equal to, approximately equal to 1. So the second derivative of t, the absolute value of that is less than or equal to 3 over 4. Because this is equal to 1, this one. Now, for m equal to 3/4, so we have the first remainder here is less than or equal to 3 over 8 times t squared. So we have to multiply this by 2 because of this 2 factorial. So 2 factorial times 4 equal to 8 here. And we have the 3. So now the difference in kinetic energy here is given by this, so by substitution. So the first remainder here times rest mass here. So by substitution, 3 over 8 t squared equal to 3 over 8 of the rest mass times b to the fourth. The b to the fourth is the speed of moving object, b to the fourth power. Then we have the second power, the square of the speed of light. So since b equal to 100 meter per second, c equal to 3, this is the speed of light, 3 times 10 to the 8 meter per second. So we have the ratio here, b to the fourth over c squared equal to 1 over 9 times 10 to the 8. So the difference now is equal to the difference between the relativistic kinetic energy and classical kinetic energy, according to the computation, is equal to 4.17 times into the negative 10 of the wrist mass. The unit here is in terms of joule because this is the kinetic energy. So we have the final answer here. for our summary, when the speed of the moving object is much, much less than c, the speed of light, the relativistic kinetic energy re- reduces to the classical form, k equals to uh, one half of the rest mass here, m sub 0 times the square of the speed of the moving object. So the maximum difference between the relativistic and classical approximation for k, when the v is less than or equal to 100 meter per second, is bounded by this value. So 4.17 times 10 to the negative 10 of the rest mass here. And the unit here is in terms the unit of the energy, the joule. So we have the mathematical simulation here. So for example, we increase the rest mass here due to the effect of the uh, special theory of relativity, because due to the effect of the increasing speed here. Then we have here, uh, if we increase the speed here, uh, the Newtonian kinetic energy deviates from the relativistic kinetic energy. So we have here, we have the deviation here. The Newtonian, the colored red, and the relativistic is the colored blue.